Hello, my name is Mohak Chadha. I'm a third year PhD student at the Chair of Computer Architecture and Parallel Systems at the Technical University of Munich. And this is my Big Data 2022 presentation on the topic FedLesScan, Mitigating Stragglers in Serverless Federated Learning. The presentation is structured as follows. First, I will give a brief introduction on FL and the problem of stragglers. Then I will discuss the contributions of our work, followed by the evaluation and our results, and finally conclude the presentation and provide insights on future work. Federated learning is a distributed learning paradigm that enables collaborative learning of ML models among a group of participants or devices without sharing their data. An FL system has two main components, that is a central server and the participating clients. The central server is responsible for coordinating the training process and contains the latest global model. The traditional FL training is done in synchronous rounds, and in each round, a subset of clients participate in the training. At the start of a round, the central server sends the latest global model to a subset of the devices to train and waits for the responses from those clients or for a specific timeout. When these devices receive the global model, they start training locally. After they finish, they push their updates back to the central server. Upon receiving the updates or when a timeout occurs, the server constructs a new global model by aggregating the updates from the clients. The process is repeated until a desired accuracy is reached. In serverless federated learning, the clients are functions that can be deployed on edge devices or on function as a service platforms. One of the major benefits of using FAST in federated learning is saving computation resources and cost from idling clients in an FL training round. Stragglers or slow clients in serverless federated learning have many common properties to stragglers in traditional stateful-based FL. The effect of stragglers is the same as clients can either take a long time to respond with their updates due to low computation power or large dataset size or even cold starts. They can also completely fail due to availability or network issues. To demonstrate this effect, we did an experiment on an open source serverless FL system called FedLess. We observed that with an increased number of stragglers in the system, the accuracy of the trained model significantly dropped. Also, stragglers can significantly increase training round times. Addressing the issues of stragglers in federated learning is a known problem, and there has been significant efforts in literature to address this issue. However, existing approaches have drawbacks that make them not suitable for serverless environments. Synchronous approaches like FedAverage suffer from increased training time when stragglers exist in the system, while other asynchronous approaches such as FedAsync have low training times but can have more computation at the client or do not work well with the stateless nature of serverless environments. Towards efficient serverless FL, we introduce a semi-asynchronous clustering-based strategy specifically tailored for serverless environments called FedLesScan. FedLesScan can dynamically adapt to the client's behavior at very little to no communication cost. To implement and evaluate our strategy, we use an open source serverless FL system called FedLess. Towards this, we extend FedLess to make it easier to use and develop our strategy. This is the original system design of FedLess, which consists of a Kubernetes-based control plane with a deployed OpenWhisk cluster. It uses MongoDB as the client database and as the parameter server. The client database holds the information about the clients, and the parameter server is a collection which contains the global model and holds the weights updates sent by the clients after each round. Another component is a controller which coordinates the training and invokes the client functions and the aggregation function. There is also an authentication server to authenticate clients participating in the round. And at last, we have the aggregation function based on OpenWhisk. As you can see, there are a few limitations. First, to use FedLess, you have to deploy OpenWhisk on top of Kubernetes, which makes it slightly hard to deploy. Second, the aggregation is only supported on OpenWhisk, so you are kind of locked into the platform. Third, the platform only supports FedAverage. And fourth, to develop and debug models, you need to deploy many client functions on actual fast platforms, which makes development significantly hard. To overcome these limitations, first, we remove the need to use Kubernetes and OpenVis to speed up the deployment. Second, the aggregator function is now generic and can be used on any fast platform. Third, we added support for implementing multiple training strategies by modifying the controller. Each strategy contains two paths, as you can see in the strategy manager, a selection scheme and an aggregation scheme. Furthermore, we added client history in the database, which collects data on the past behavior of clients, such as training time and the missed rounds. Furthermore, to enable ease of development, we implemented a mocking system in FedLess to simulate the platform as a whole on a single machine. For debugging, clients and aggregator processes can run on a single machine without the need to deploy the clients on actual fast platforms. The developer only needs to specify the mock flag while running the controller, and the rest is handled automatically by the mock invoker. This enables faster development of new strategies. Moving on to FedLesScan. Our strategy contains two parts. First, an intelligent client selection algorithm based on dbScan clustering. Second, a Staleness-Aware Aggregation scheme to asynchronously aggregate delayed client updates. Our intelligent client selection scheme contains few features that clearly distinguish it from the other approaches. First, the algorithm is based on dbScan, which unlike other clustering approaches does not need the number of clusters to be determined before training. Second, the algorithm is very efficient with a worst case complexity of n log n, where n is the number of clients, making it suitable for large scale FL systems. Also, our approach considers failures and slow updates such that we group clients with similar behavior together to minimize the effect of stragglers on the rest of the clients. So how does it work? So our strategy partitions clients into three tiers, that is rookies, participants, and stragglers. Rookies are clients which have not yet participated in the FL training process and for which no behavioral data exists. Participants are the group of clients that can participate in the clustering process. Stragglers are clients that have missed one or more consecutive training rounds. These clients have the lowest priority in our client selection process. To better explain our selection strategy, assume that all clients are in a jar. This jar can be further divided into three jars based on the tiers we just mentioned. The rookies jar contains the clients which have never been invoked before. Essentially, all clients are rookies in the beginning. The second jar contains clients which participate in the clustering process, and the third jar contains the unreliable clients. For client selection, the jars are ordered based on their priority. The strategy for picking the clients differs for the three jars. We use random selection for rookies and stragglers, while the second tier clients are selected based on clustering. The priority aggregation function does the following. It takes clients from the first jar and then moves on to the next if there are not sufficient number of clients available. Moreover, as the training progresses, the clients can move between tiers. So after a few training rounds, the rookies jar will be empty when all clients have been called at least once. We now have a few of them in the second and the third tiers. During the training, we move clients between these tiers based on a cooldown variable. This is set to demote clients which fail for a certain number of rounds to the third tier. Once it expires, they can move back to the second tier. So how does the clustering actually works? For clustering, from the second tier clients, we collect their training times and their missed rounds. Following this, we compute a penalty factor called missed round ratios by dividing each round in the list of missed rounds by the current round. This factor gives a higher penalty to clients which miss recent rounds. Next, we do an exponential moving average on both lists and get a single value for both training EMA and missed round EMA. We use these features for clustering. We provide a way to automatically tune the parameters of DBScan to give the best clustering. After we obtain the clusters, we compute the total EMA for each client by adding the training time and the penalty time. We then sort the clusters and pick clients closer together to participate in the training. To accommodate slow updates from clients, we provide a Staleness-Aware Aggregation scheme that includes past updates but with a dampening effect. The aggregation is triggered at the end of each round. So instead of finding only the most recent round results in the parameter server, we fetch all updates newer than a certain tunable parameter tau. Following this, we aggregate the updates according to the shown equation. Moving on to our evaluation results, we use 4 data sets from 3 different benchmarks, all non-IID. The tasks include image, text, and audio to make the results more conclusive. On each dataset, we experimented with several scenarios with various straggler ratios in the system from 0% to 10, 30, 50, and 70% stragglers. We do that by selecting a random subset of clients to fail during training. For delayed updates, we decrease the round time so that few clients will have to push their updates after the round ends. All clients are deployed using the second generation Google Cloud functions. For evaluating our strategy, we use a wide variety of metrics: the accuracy of the trained model, the contribution of the clients, which is measured by the effective update ratio. EUR represents a ratio between the clients which finished the training round successfully and the clients selected for that round. Total training time, for this we assume worst case scenario where stragglers time out at the end of the round. The cost is measured by estimating the function cost using the Google Cloud cost model. We evaluate our strategy against the popular FedAverage and FedProx approaches. Overall, FedLesScan achieves faster conversions as compared to the other 2 strategies. On the right, we show some results for the Google Speech datasets. For the standard and scenario with 70% stragglers, our strategy achieves faster convergence with higher accuracy. Across all datasets and scenarios, our strategy achieves 2% higher end accuracy. Moreover, our strategy utilizes clients significantly better with an average increase in EUR of 17.75%. Drops in EUR values show the effect of clustering of the clients. Distributing slow clients across the training rounds will affect the efficiency of more rounds. Overall, our strategy reduces the total training time by 8% on average. The values in these plots are averaged across all experiment scenarios for a particular datasets. Finally, our strategy leads to 20% reduction in training costs and average across all datasets and scenarios. To conclude, we made several extensions to an open source system and framework for serverless federated learning called FedLess. We proposed and implemented a semi-asynchronous FL training strategy tailored for serverless environments. We extensively evaluated our strategy on a public cloud platform against 2 other popular training approaches. In the future, we plan to investigate the use of more advanced staleness-aware aggregation schemes. Moreover, we plan to explore dynamically adapting the number of clients selected in each training round in FedLesScan based on the current system state. Thank you.